Okay. Today we're going to talk about the Lorenz force and a couple of special cases of it. So, Lorenz force applications. We'll remember what the Lorenz force is. It's the force from a magnetic field on a charged particle. So it's going to be F equals QV cross B. So it's going to be a force that is perpendicular to perpendicular to the direction of velocity and the magnetic field. So I'll give you an example to kind of give you a feel for how this is going to work. Let's say we have just any force or any positive particle. It's moving this way, and it's in a field that goes into the page. So we'll make a big field. We want it to go all the way through here. We're going to make it all the way around. So we've got a field that goes like that. Okay. So the field goes like that. My thumb goes to the left, and my fingers go into the page, or my fingers go down into the page. So that means that the force on it, the force will be down. So if there's a little bit of force like that, in my next phase, I'm going to have a velocity that's going to be pointed a little more this way. Well, if I repeat the same process, where I have if I repeat the same process, now I'm going to have a thumb pointing down and to the right. I'm still going to have my field pointing in. I'm going to end up with something that goes, I'm going to end up with a force that goes like that. Okay. So what's going to happen is my path, if that continues, if my field continues to be down here, the next one is going to be like that. Okay, but my direction, my velocity is going to be a little bit closer to that. Then the direction of my force is going to be a little closer to that. And then you can see what's going to happen here, which is that I'm getting a path that looks an awful lot like looks an awful spot like a circle. And that's what's going to happen. Since we have a force that's going to be perpendicular the entire time to the motion of it, just like the force on from a rope is perpendicular to the motion of a something whirling around in a horizontal circle the whole time, what we're going to get is we're going to get a path that makes a nice circle all the way around. Okay? And that's going to be our path. Okay. Now, how do we determine some things about that is the next question. So, well, it's a centripetal force. So what that means for us is that this, and I'm just going to use the magnitude of it, that QVB. Notice I'm not using the sine of theta because it's because we already know they're perpendicular. Equals mv squared over r is a centripetal force. Okay, one of these divides away, and I have a QB R equals mv. I multiplied both sides by r. Okay, and I get that r, the radius, equals mv over qb. I'm solving for an expression for radius, and that sort of makes sense if you think about it, because if it has a bigger mass, then that's what's gonna then if they have a bigger mass, you get a bigger radius. It'll be harder to stop it. It'll have more inertia. It's going faster. It'll have a bigger radius also. And it's going to be harder to keep it in that circle with your magnetic field if you have that. If you have a bigger charge, it will be a smaller radius because the force will be bigger. So the force, since the force is larger, that'll make the radius tighter. Same with the magnetic field. You'll get a much larger force if you have a larger magnetic field. That's going to lead to a smaller radius. There's a lot of situations that's helpful, and many of them are chemical related. If you took AP Chem or any chemistry in college, and you had a and you used the Spec 20, the spectrophotometer, that's how it works. It actually takes the particles and the singularly ionized particles, which are basically like +1 particles. It puts them through a magnetic field, and it looks for it sends them in a straight line, and then it looks for the radius where they collect. And based on that radius, it's able to tell what kind of particles they are and how many of them strike. And they can give you an idea like what the composition of the material you put into the spectrophotometer is. It turns out there's also a way to, back in the old days, and by the old days I mean like the late 30s, early 40s, when they were building the initial fission nuclear weapons, they needed to separate out the different isotopes of uranium. Since U-235 was the one that was more fissile, the one that was more usable as a nuclear weapon, than U-238, which was the most common one. But there are only 3 U-235 atoms for every 1,000 atoms by mass in any sample of uranium. So they did the same thing. They heated them all, and they put them in this, I think they call it a cyclotron or something like that. And they managed to separate the particles that way as well. Okay. Now, all the rules that go with centripetal force work here. So instead of substituting mv squared over r, you could have done m times 4 pi squared r over t squared if you need to get the period. It works the same way, but it's the same centripetal force. Okay. You just wouldn't divide out the velocity, which makes it harder. I think it's a lot easier if you have these problems to solve with the velocity and then substitute the linear velocity equation, 2 pi r over period instead.